Senior Laboratory Technician, Infrared Spectroscopy Lab. I'm going to take you through the InvenioS HTS-XT Spectrometer, the do's and don'ts and how it works. There are 6 critical things you need to understand before you start operating the InvenioS HTS-XT. First, the instrument has to be connected in a stable power supply. For that, we're using the UPS, the uninterrupted power supply. And there's a sequence that needs to be followed when you switch on the instrument. First, you switch on the InvenioS, followed by the HTS-XT, and then the CPU. It's important to note that the HTS-XT power is linked to the CPU. Okay? Another thing you need to do before you start operating the machine is you need to make sure that the mercury cadmium telluride MCT detector is cooled down to liquid nitrogen temperatures. That's about negative 196 degrees Celsius. So we'll just cool down the detector before we start operating the instrument. The reason as to why we are cooling down the MCT detector, if the detector is cooled down, the spectra that we are going to get won't have the thermal noise. They are going to be very smooth spectra. That's why it's important for the detector to be cooled down before you do your measurements. Cooling down of the detector should be done after every 4 hours. Just to make sure that the spectra you are generating while running the instruments are of good quality. You will notice that the nitrogen is filled up when you start seeing nitrogen coming out of the vat. After topping up liquid nitrogen, it's recommended that you wait for about 5 minutes for the detector to be ready before you start running your samples. The instrument has got 3 desicants. It has a desicant here. Another desicant is placed here near the interferometer, and the 3rd desicant is placed here just next to the light source. So you need to make sure that the 3 desicants are regenerated and so that the instrument does not have moisture before you operate the instrument. Usually regenerate the desicants on a monthly basis. Generally, and to do that, you just put the desicants beads on a beaker and then you place them in the oven at 150 degrees for 24 hours. The light source need to be replaced after around 3 to 5 years when the instrument is operating. Once you replace the light source, it's important that you have to do the validation tests, and then you also run the laser wave number tests before you start using the instrument. Okay? We highly recommend you review your spectrums before further processing to help monitor water or moisture peaks at about 3,960 to 3,480 centimeters wave numbers, and also below 500. And you can also check out for the CO2 absorption peaks levels at about 2,360 to 2,339 centimeters wave number as part of a quality control checks. Although the CO2 can be removed during data pre-processing. The spectral data generated from the instrument are saved and further processed using shared C4 aircraft spectral processing and analysis tools and methods. You can check out for the same on our website link. Samples must be fine ground to 0.05 millimeters and loaded on these aluminum plates before you start running them. You can see the aluminum plate. The aluminum plate has got 96 wells. The first well has a gold. That's for our background measurements, reference measurement. The second well is a blank. That's for our blank. And then thereafter now we load our standards before loading our samples. So usually the A1 is the gold, the B1 is a blank. From C to H1, those are our standards. Now the first sample starts at well number A2, and we normally load the samples in duplicates. That means that well A2 and B2 have the same samples because we are loading them in duplicates. And the final wells, the well H12 and G12 also have a standard, our white sand standards. So the first row has got our standards, and the last two wells also have got our standards. The samples are in between. The loaded aluminum plate is accompanied by a recording sheet showing the sample serial numbers of the samples that have been loaded on the plate. Yeah, it's the same thing as you can see on the recording sheet. The first row we have our background blank, and then our standards, and the last one is also our standard. The last two wells are also having our standards, and the sample in between are the samples that we are analyzing. So this data on the recording sheet, it relates to exactly what we have here on the Excel. Yeah? As you can see, what we have here is plate 4, which is this plate 4 here. Each plate holds 43 samples. So for the plate 4, it starts from this lab ID that ends with 784. That's where it's starting, all the way up to 826, which is this last sample. So what we are going to do, we are going to transfer this data from the Excel to our Opus lab, which is where now the plate is going to be synchronized. Whereby now when we slot in the aluminum plate into the Opus, into the HTS-XT, it's going to synchronize with the data that is on the Opus. Let me just show you how to do it. So you just copy the plate 4 and then you paste it on to the Opus lab here. As you can see, we just paste first. Paste here. Here now we have in Opus lab, as you can see, these are the wells and these are the lab IDs of that particular sample. So that's how they are going to relate. So I'll just save this work as a template so that when the instrument is running, it will be running as per the instructions of this template. So we will save it as plate 4 on a folder that I had already created of that particular task. We have guitar, plate 4, save. Okay, we've already saved it. Now we have it as a task. Now we are going to slot in the sample and run the test. But before we do that, there's one last test that we need to do, which is checking the signal to make sure that the signal count that we're getting from the instrument is high enough to be able to take measurements. To do that, we use an empty aluminum well. Yeah? I'll just do that right now. I'll load the template for taking the signal. So the drawer will automatically open here for us to slot in the empty well. Yeah. So this is the empty well that we are going to use to measure the signal counts. I'll just slot it in. You'll notice that when you're doing that, the Opus lab is giving you instructions. It's telling you once you've slotted in the empty plate, you should click OK so that it starts doing the signal check. We've already done that, so I'll just click OK for the door to close and for it to take the signal check and give me the results. A good signal should be of about over 10,000 signal counts. Anything below 10,000 shows that you did not top up liquid nitrogen properly. So you'll have to top up liquid nitrogen again. And it doesn't take long, it takes like 30 seconds for you to get the results of the signal check. As you see, we already have the results of the signal check. They are the correct results. We have a count of over 10,000. So I'll just click yes to save the signal count, and the drawer will open for you to remove the plate. Yeah, so now I'll just close the drawer, and the instrument is now ready for us to start our run. Yeah. So the next step will be now to load the template of the fourth plate that we had created. I'll just come here to load sample and look. I'll go to the folder where I've saved the template for the fourth plate, which is this one here. I've selected the fourth plate, and then I click on measure, and then I click on measure again. The drawer will automatically open. So what will be happening? The instrument will be scanning a well at a time. It will be like taking the background measurement using the gold, then scanning the well. Taking the background measurements before scanning the well. So it will be moving back and forth. Before scanning each well, it will be taking the reading of the background measurement. Yeah. Once it has finished scanning a well, that well will turn green, like what you are seeing. It will be a green dot. This shows you that it has completed scanning the well. A successful completion of scanning a plate, you will have all green dots on this particular page. In case you have green dots and then it reaches a point you have red dots, that's an indicator that there's a problem. Most probably you needed to top up liquid nitrogen and you didn't. Now when you look at the spectra with the samples with the spectra with the red dots, basically what you will see are noise. They won't be good quality spectra. Yeah? So that's something that we usually look out for quality control checks. A successful run will have green dots on all the 96 wells. Each well holds 43 samples. Yeah? And in a day, the instrument has a capacity of running around 10 plates, which means in a day we can successfully run 430 samples in duplicate. After you've checked your signal, and let's say the signal was below 10,000, which means that you didn't top up the liquid nitrogen well, the signals you are going to get are going to be poor quality. Regardless, the dots might be green, but the signals that you're going to get are not going to be of good quality. Yeah? They are going to be of poor quality. Immediately the wells start showing red but not green, it means that the problem is worse. But still, you can be able to tell if you didn't top up liquid nitrogen properly if you look at the spectra. For example, let's look at these ones. A case scenario whereby we didn't load liquid nitrogen properly. As you can see, the detector is giving a very poor quality spectra with a lot of noise. This is attributed to liquid nitrogen. You didn't cool down the MCT detector well, so now the spectra that is generating are of poor quality, and they have a lot of noise. Yeah, and that's it. Upon completion of the plate, we will create a template for the next run and slot it in. Switching off the instrument is actually the reverse of switching on. First, you'll have like to get out of the upper slab software. Then you shut down the computer. After shutting down the computer, you'll have now to switch off the HTS-XT, and finally you switch off the Invenio. That's the sequence that you follow when you are shutting down the instrument.